Welcome to CSAI Think Tinker Learn. This is part of System Design Essential series, where we build solid mental models to how systems actually function. Today, we are tearing apart query optimization and execution plans. Before we dive into the engine block, please hit that like button, share this video, and subscribe to support the channel. This series is paired with articles and on a companion site at uh, CSAITTL. Let me bring it up 1 second. This is the site CSTTL GitHub IO. This is the GitHub pages. Again, it's a work in progress site. It has list of article as and when the more articles come along, I'll post them here and we'll continue making the videos. Okay. As I mentioned earlier, we keep these videos, this series video particularly, the System Design Essential series, um, at a very high level to give the architecture big picture very quickly. If you want a lengthy deep dive on anything, something really specific, whether in this particular video or from any other system design topic, please let us know in the comments and we'll make sure that we actually get that video across to you. Let's stop guessing why queries are slow and see how database actually works. When you send a query, it travels through a macro pipeline of 4 stages essentially. Stage 1 is the parser. It checks syntax in memory. Stage 2 is the rewriter, which expands your views and subqueries. Most engineers think their SQL goes straight from here to the executor, but it doesn't. Stage 3 is the optimizer, which is the star of our show. This is where the magic and the disaster happens. The optimizer evaluates thousands of possible paths based on the cost before handling the final map to the executor. This, sim- who, this executor simply follows instruction without thinking anything at all. To understand the optimizer's brain, we have to look at the evolution from rule-based to cost-based. Rule-based optimization uses blind predictable checklists like always use an index if it exists. It fails catastrophically when an index scan is actually slower than a full scan. Modern engines like PostgreSQL and MySQL 8 plus use cost-based optimization. It uses data-aware probability routing, evaluating the cardinality or uniqueness of data to find the mathematically cheapest path. When you look at an execution plan, stop reading it top-down like an application code. The database executes the deepest indented nodes first. You start at the leaves and follow the data flow upward. In this plan, we see two sequential scans feeding into a hash join. The cost isn't measured in seconds, but in abstract units of work. The first number is the startup cost, the time to get the first row, and the second is the total cost to return everything. There's a massive difference between the simulator and the track. Explain is just a prediction. It tells you what the database thinks it will do. The keyword is thinks. Explain analyze actually executes the query and measure the real-time performance. If your estimated rows diverge widely from the actual rows, it's a massive red flag. It means the optimizer statistics are stale and it is making confident decisions based on total lies. The first category of the plan is table access methods. A sequential scan is brute force, reading the entire heap. It, it is actually efficient for reading more than 10% of a table. An index scan is faster for small lookups, but requires a random IO jump to the heap to get the full data. The holy grail is the index-only scan. If you have a covering index that contains all the columns you need, the engine never touches the heap at all, leading to peak performance. Next, we look at the join strategies. Nested loops use low memory but enter a death spiral if an inner table isn't indexed. Hash joins are the workhorse for large unindexed tables. The engine builds a hash table in memory for O1 probing. Merge joins are incredibly fast but require both inputs to be pre-sorted. The optimizer picks the strategy based on your data volume and available memory. Memory management is the silent performance killer. Sorts and hash aggregates are fast until they run out of work mem. If your execution plan says batches greater than 1, your memory bucket overflowed and the data is spilled onto the disk. Disk I/O is 10 to 100 times slower than RAM. If you see this, you need to increase your work memory setting for that session to keep the engine off the physical disk. Statistics are the fuel of optimizer. It cannot see your actual data. It only sees statistical buckets like n underscore distinct, which is the cardinality, and n null underscore frac. It is a fast query suddenly begins to crawl, your statistics are likely stale. Before you start blindly adding indexes, run an analyze command. It refreshes the optimizer's worldview so it can make better decisions. A major hurdle is the correlation trap. The optimizer assumes columns are independent. If you filter by city and the zip code, the math says the result set should be very small. But in the real world, these columns are highly correlated. The optimizer picks a plan for one row but gets hit with 50,000. In these cases, you need to use extended statistics to tell the database that these columns move together. Developers often accidentally defeat the optimizers. This is the function trap. If you have an index on email, but you write where lower email equals test at test.com, you have put a concrete wall in front of the high-speed lane. The optimizer cannot look inside the function, and it forces a slow sequential scan. To fix this, you must use functional indexes or keep the predicates clean. The problem always isn't inside the database. Sometimes it's the application code loop called the n plus 1 problem. Fetching 1000 customers and then firing 1000 tiny pings over the network to get their orders will saturate your network and create massive latency. One optimized join with a single round trip is almost always faster than 1000 tiny pings, regardless of how fast your database is. Common table expression or CTEs used to act as the optimization fence. In older version of Postgres, a CTE was materialized, which is save to disk, by default, which could block the optimizer from pushing files down. In modern versions, CTEs are inline by default, meaning they behave more like subqueries. Understanding whether your CTE is fenced or inline is crucial for complex reporting queries. Here's your senior engineer diagnostic cheat sheet. If you see a sequential scan on a large table, you're missing an index. If estimates don't match reality, your stats are stale. If you see batches greater than 4 on a sort, you're spilling through the disk. Memorize these red flags to move from guessing to surgical fixing. To wrap up, Optimizer is probabilistic reasoner with a finite budget. Don't fight it. Give it a better information through clean predicates and fresh statistics. Now, I have a question for you. What is the weirdest or most nonsensical execution plan you have seen the optimizer choose? Share your stories in the comments. If this helped you understand the engine block better, please like, share, and subscribe to CSAI Think Tinker Learn. And please click on that notification icon so that you can watch other video or whenever we post a video, it gets to you. Check out the site for more essentials. Until next time, thanks for watching. Bye.